Good day everyone, I am Charlene Isabel Santiago from BSCE 13 and together with Group 5, we are going to discuss the topic that was assigned to us, CuO or copper oxide for supercapacitor. As we are tasked to find a reliable journal article regarding the topic assigned to us, our group has decided to choose the article entitled Surfactant-Assisted Cabbage Roast-like Copper Oxide Deposition on Copper Foam for Supercapacitor Applications by P.E. Lokhande and Umesh S. Chavan. This was published online on February 14, 2019. Today, we will talk about the journal article's introduction, methodology, results and discussion, and the conclusion. Next slide, please. Before we start with the introduction part of the study, let us first familiarize ourselves with the definition of terms. Nanostructure, a structure, especially semiconductor device that has dimensions of only a few nanometers. CuO or copper oxide is an inorganic compound with the formula CuO, a black solid in color, and is one of the two stable oxides of copper, and the other being Cu2O or copper 1 oxide. As a mineral, it is known as tenorite. Next slide, please. Surfactant. These are compounds that lower the surface tension between two liquids, between a gas and a liquid, or between a liquid and a solid. Surfactants may act as detergents, wetting agents, emulsifiers, foaming agents, or dispersants. Supercapacitor, or SC, on the other hand, is also called an ultracapacitor. It is a high-capacity capacitor which capacitance value much higher than the other capacitors, but with lower voltage limits. It bridges the gap between electrolytic capacitors and rechargeable batteries. Next slide, please. As the world's population grows, so does the demand for petroleum fuel. Global economic progress necessitated the development of sustainable, clean energy resources and conversion and storage technology. Batteries, fuel cells, and electrochemical supercapacitors have recently proven the most effective energy conversion and storage technology. Because of their high power density, adequate energy density, and extended life cycle, supercapacitors are the most promising candidate among them. The use of less active material and poorly regulated porous structure limit commonly developed electrodes for supercapacitors, which are made by spreading a paste of active conductive carbon and conductive polymer to the current collector. A new binder-free electrode material is required to address this issue and boost energy density. Supercapacitors are classified on the basis energy storage mechanism. First, the electrochemical double-layer capacitor or EDLC. It stores energy non-ferritically by accumulating charge at the interface of electrode-electrolyte. Carbon-based materials like activated carbon, carbon aerogels, graphene, and carbon nanotube in EDLC. Second, we have pseudocapacitor, transition metal oxide like ruthenium 4 oxide, copper oxide, nickel 2 hydroxide, manganese dioxide, and others are widely investigated in this. Next slide, please. Many studies have lately concentrated on enhanced methods for direct copper oxide deposition on conductive substrates such as copper foil, copper foam, nitrogen foam, glass, and stainless steel. This material serves as both current collector and the substrate. In here, we will see that Donghi et al. Synthesized nanostructured CuO to Cu2O on copper foam by anodization method, which exhibits specific capacitance of 1.954 FMC squared. The nanostructured materials with high surface area and porous nature allows high reaction rate, which leads to excellent electrochemical performance. Therefore, significant research focused on design and fabrication of nanostructured electrode with different morphologies for supercapacitor application. The synthesis of nanostructured copper oxide with different morphologies attracted wide interest owing their high electrochemical performance. Next, we also have Wiley et al. They formed copper oxide nanosheet, nanowires, and flower on copper foam. The CuO nanosheet showed higher specific capacitance, which is 212 Fg1, the nanowires, and flower-like structure. We also have here Zhang et al., which synthesized flower-like nanostructured MnO2-coated CuO via a hydrothermal method, which specific capacitance 167.2 Fg-1. Lastly, we have Dubal et al., which have developed micro-roses woolen-like nanosheets of copper oxide on stainless steel, which exhibited specific capacitance of 346 Fg1. Another experiment, they reported nanostructured CuO with different morphologies, woolen clump, stacked nanosheet, and nanobuds developed on stainless steel by chemical deposition method with surfactant. 3D framed nanostructure of nanobuds of CuO demonstrated specific capacitance of 396 Fg1, higher than other morphology. Next slide, please. In here, we can see Table 1. Table 1 explains synthesis of copper oxide in diverse morphology using different methodology and their performance in one glance. In this work, surfactant-assisted nanostructured copper oxide deposited on copper foam by simple and effective chemical deposition method. Compared with conventional copper oxide with HMT forms cubic morphology, surfactant-assisted CuO exhibited cabbage rose-like structure. The specific capacitance obtained for surfactant-assisted CuO obtained high capacitance and excellent cycle stability. The organic surfactant plays a vital role in prepared material structure and morphology. Hence, it is clear that the unique nanostructure of the compound can be created using dispersion and self-assembly of surfactant, colloidal suspension, and protein. It can be achieved with a simple and effective chemical deposition method by surfactant-assisted nanostructured CuO deposited on copper foam. Compared with conventional copper oxide with HMT forms cubic morphology, surfactant-assisted copper oxide can exhibit a rose-like cabbage. To explain further the study, we have Friedrich Loredo for the methodology.
Good day everyone. I'm Friedrich Loredo from Group 5 of BSCE 13. So for the methodology, using a chemical vapor deposition technique with heat treatment, several kinds of nanostructured copper oxide were created on 3D network copper foam. All of the compounds are analytical grade reagents that haven't been purified further. To eliminate contaminants, a 2 by 2 cm 2 copper foam was carefully washed in an ultrasonic bath for 10 minutes with 1 mole of hydrochloric solution, then ultrasonically washed with acetone, 100% ethanol, and deionized water for 10 minutes. Next slide, please. 0.798 grams of copper sulfate was dissolved in 50 ml deionized water for the nanosheet manufacturing procedure from copper oxide, and then 0.7 grams of methenamine was added to a homogeneous solution with continuous stirring. Triton X100 has been added to the aforesaid solution as a structured non-ionic organic surfactant with a weight of 1%. The substrate was copper foam that had been weighed before being utilized. Next slide, please. The copper foam was then immersed in the prepared solution, which was then transferred to an electric furnace at 70 degrees Celsius and wrapped with aluminum foil. For hours, the copper oxide deposited copper foam of the collected final product was then cleaned with ethanol and deionized water before being calcined at 200 degrees Celsius. All 20 to 80 data points were taken at a sampling rate of 10 minutes. One using an X-ray diffractometer which is equals to 0.15405 nanometer, and using copper K alpha radiation, which is equals to 0.1541 nanometer. X-ray diffractometer or XRD allows one to ascertain to the molecular structure of a crystalline material by diffracting X-rays through the sample. X-ray diffractometer analyzer obtains interference patterns reflecting lattice structures by varying the angle of incidence of the X-ray beam. Using a scanning electron microscope or SEM, the morphology of the electrode material was revealed. The SEM is a microscope that uses electrons instead of light to form an image. The scanning electron microscope has many advantages over traditional microscopes. The SEM has a large depth of field, which allows more of a specimen to be focused at one time. Next slide, please. In the range of 4,000 to 400 cm to the negative first power, a Perkin-Elmer Spectrum 100 spectrometer was used to perform Fourier transform infrared or FTIR spectroscopy. What is FTIR spectrometer used for? FTIR spectra reveal the composition of solids, liquids, and gases. The most common uses is in the identification of unknown materials and confirmation of reduction materials, whether it is incoming or outgoing. The information content is very specific in most cases, permitting fine discrimination between like materials. Using cyclic voltammetry and constant current charge or discharge technology, the ultracapacity of a thin copper oxide membrane electrodeposited on copper foam was investigated with 6 KOH electrolytes. Cyclic voltammetry or CV is the most popular electrochemical technique due to its ability to deduce reaction mechanisms with relatively low-cost equipment and quick experimentation. Cyclic voltammetry can be performed with a general-purpose potentiostat like the Gambri interface 1010B. For this copper oxide, copper foam working electrode, a traditional 3-electrode electrochemical cell was used. The counter electrode was made of platinum foil, whereas the reference electrode was made of SCE.
Slide was the film formation and reaction mechanism. It is the inclusion of organic surfactant agents to the chemical deposition technique or CDM allowed for the creation of various morphologies of copper oxide. The solid phase in CDM is created by dividing a supersaturated solution into two stages once it has reached saturation. Nucleation was achieved in the first step by quick disintegration of the cluster of metal precursor molecules and subsequent particle development by coalescence of particles on the substrate via a heterogeneous process. As a source of copper 2+, copper sulfate was employed. There was no precipitation of HMP when it was introduced to the copper sulfate solution, unlike ammonia or other complexing agent. Copper foam was used as the substrate, which was submerged in the solution and held at 70 degrees Celsius. Because of the partial hydrolysis of HMT at higher temperatures, formaldehyde and ammonia are produced. Next slide, please. The ammonia produced by the hydrolysis of HMT was reacting copper dioxide precipitates when copper 2+ is combined with it. Further, by generating complex ions, ammonia inhibits precipitation. As the reaction progresses, the concentration of OH negative increases, which is usually beneficial to the formation of copper oxide. Copper NH342 releases H2O and NH3 at higher temperature, resulting in the production of copper oxide. In the second reaction, organic surfactant was combined with the complexing agent HMT, but Triton X100, which works as a structure guiding agent, was not included in the reaction. The first figure shows the XRD spectra of chemically deposited nanostructured copper oxide presented under different conditions. All peaks at 2H angle values of 36.3, 42.36, 61.48, and text to play negative 111, 220, and 202 respectively confirms the formation of monoclinic copper oxide based on reference data JCPDS card number 4120254 without any other impurities due to the active material deposited in the copper foam gave 3 extra peaks at 2H values of 43.4, 50.56, 72.2. The addition of organic surfactant significantly changes in the intensity of the XRD peaks. Next slide please. Figure shows the diffraction peak at 2H values 35.84, 36.3, 38.92, 49, 58.4, 61.64, and 75.68 corresponding to lattice planes 002, negative 111, 111, 200, negative 202, 113, and 004 respectively, which indicates simple monoclinic copper oxide. Addition of surfactant leads to increase in intensity and width of the peaks indexed at negative 111 and 111, which suggests the formation of crystalline particles. Next slide. One is the surface morphological studies. Figure 2 shows SEM images of bare and surfactant-assisted copper oxide deposited in copper foam. The SEM images of copper oxide nanocuboid morphology in different sizes cover the entire copper foam skeleton synthesized without the addition of surfactant. The approximate dimensions are length is equivalent to 7.24, width 6.188, and height 13.84. Simply by the addition of Triton X100 surfactant, nanocubes turn into nanoflower-like structures. Organic surfactant structure directing property causes morphology to change. Surfactant provides a different degree of aggregation and grain size, leading to a different micro-nanostructure. Nanopetals having a thickness of approximately 5 to 7 nanometer connected to each other form a cabbage rose-like structure that provides micro and bisulfurous surfaces for electrochemical property enhancement. Triton X100 molecules contain polyethylene oxide and aromatic hydrocarbons, and these molecules are responsible for the formation of hydrophobic and hydrophilic regions. Hence, the growth process in the presence of organic surfactant is arbitrated by the nanoscale segregation of organic rich and organic clean domains on the growing copper oxide nanoparticles. This segregation leads to the formation of a 3D flower-like structure. Next slide. The next one is the FTIR study. The chemical properties of copper oxide synthesized by the CDM method have been studied by FTIR spectroscopy in the presence and absence of surfactant. As shown in figure 3, the strong absorption peaks observed for each sample in the range of 800 to 1200 cm due to the stretching of copper oxide revealed the vibration of copper oxide nanocrystals. The carbon-oxygen stretching vibration present in TRX100 was responsible for the formation of the strong peak at 1096 cm because of the presence of atmospheric CO2. Peaks observed in the range of 1350 to 1700 cm. Peaks were generated at 2900 to 3500 due to humid air and hydrated copper oxide. The FTIR spectrum of the surfactant shows broad OH stretching at 3,281 cm because of the Triton X100's non-polyether chain with an OH group. The FTIR spectrum also indicates organic surfactant, less formation of copper oxide. The next slide will be discussed by Ate Rani Lingjoy.
For the electrochemical study, cyclic voltammetry test was conducted to measure electrochemical performance. The nanostructured copper oxide or copper electrodes. Figure 4A and B shows the CV curves of copper bare and copper TRX100 electrodes at scan rates 5, 10, 20, and 50 MVS. The potential window for both electrodes was 0 to 0.44 voltage. The profile of CV curve showed indistinct oxidation and broad reduction peaks, which clearly indicate curve indifferent from the ideal rectangular CV profile of EDLCS. Next slide, please. The pseudocapacitive behavior of copper oxide electrode was due to the complex redox reaction of copper oxide and in potassium hydroxide solution as follows. Next slide, please. The specific capacitance was calculated by using the following equation below, where IV is the instantaneous current, M is the active mass deposited on foam, V is the scan rate, and VI and VF are the potential window of the voltammetric profile. The high capacitance, the highest specific capacitance calculated for bare copper oxide and copper oxide TRX corresponding scan rates 10 MVS were 118.5 Fg and 150.6 Fg respectively. The galvanostatic charge discharge curve for copper oxide bare and copper oxide TRX at current density 5 MAS are shown in figure 4C and D respectively. These curves are not triangular in shape. It shows that pseudocapacitive behavior of copper oxide. During this charge profile, a abrupt voltage drop is due to the equivalent series resistance of the testing system. Next slide, please. The specific capacitance of copper oxide is evaluated from GCD curve by using the following equation. CS is equals I triangular T over M triangular V, where triangular T is the discharge time, I is the constant discharge current, M is the mass of deposited materials, and triangular V is the potential drop during discharge. And the specific capacitance measured for copper oxide bare were 159, 136, 113, and 91 Fg, while copper oxide TRX were 550, 295, 351, and 312 Fg at current density 30, 40, 50, and 60 Ag. Next slide, please. Figure 4E displays specific capacitance as a function of current density for copper oxide bare and copper oxide TRX. As current density increases, the specific capacitance decreases, made due to the inaccessibility on active sites at faster reaction rate. The cabbage rose-like structure offers a favorable inner space, which increases surface area, easy diffusion of the electrolyte, and the mesoporous structure allows easy access for OH, resulting in low resistance redox process. The result exhibited shows that prepared material could be applied for supercapacitors. Next slide, please. And for the conclusion of this presentation, copper oxide nanostructures have been extensively investigated and have recently attracted the attention of material scientists and engineers because to their intriguing features and prospective uses in a variety of industries. The influence of numerous parameters in the synthetic process as well as certain distinctive features and potential uses of copper oxide nanostructures are summarized in this work. We'll look at the variety of chemical synthesis methodologies as well as the influence of the fundamental components in the copper oxide nanostructure production process as well as their intriguing basic features and applications. Understanding the manufacturing method and properties of copper oxide nanostructure is critical for realizing copper oxide nanostructure application in everyday life and technology. Copper oxide nanostructure have a number of unique features that set it apart from other transition metal oxides. Copper oxide nanostructures have certain possible applications which are discussed. Next slide please. Two different copper oxide nanostructures such as cuboids and nanoflowers have formed in copper foam in this experiment, which was done with copper foam. XRD studies and FTIR shows the production of monoclinic copper oxide. When surfactant is introduced to the second solution, it functions as a direction-driven property in morphology, causing the cuboids to change into cabbage roses. Copper oxide bare and copper oxide TRX electrodes were found to have specific capacitances of 159 and 550 Fg, lat scan rates 30, respectively in potassium hydroxide electride. And that's it for this presentation, and again we are the group 5 from BSCE 13. Thank you po.